All right, the last thing we need to look at is this thing called roots of unity. So basically we're talking about z to the power of n plus or minus 1. Plus or minus 1. Most of the time it'll be plus 1 we look at. So any equation in that form, what we call the nth roots of unity. Now, if you were to plot them on an Argand diagram, they'd all sit on the unit circle because the modulus would end up being 1. And if you were to join them all up, you'd get a regular polygon, because remember, solutions are symmetric around the circle. So let's try z to the power of 5 is equal to 1. So using our idea we saw with de Moivre's, notice I'm using conjugates because it is a real number we're finding here. So I know the solutions will be in conjugate pairs. So I'm going to sub in with my consecutive numbers plus or minus. So first one 0, then plus or minus 1, plus or minus 2. That gives me 5 solutions. And so the first one is cis 0, obviously. 1 to the power of 5 is 1. And then the next one, cis 2 pi and 5, because cis 2 pi is a solution, so is cis minus 2 pi and 5, so that's the plus or minus 1. And then cis 4 pi and 5, and because cis 4 pi is, so is minus 4 pi and 5, and that's the plus or minus 2. So there's our 5 solutions. Now, I could do that very easily because, as I say, we know 1's a solution straight away. So if I draw my cis 0 there, and I know they're going to go around the unit circle, it's symmetrically. So because cis 2 pi and 5 is the next one, so would its conjugate be. Then I'd go to 4 pi and 5, its conjugate's there, and there we go, we get a pentagon. So we're always going to have conjugates, so 2 of them will be reflections, and another 2 reflections, and of course the solution 1 on that one. That's it, fits nicely on the unit circle there. All right, so we've found our 5 solutions. These are the sorts of questions they like to play with. So omega is going to be one of those complex roots. Now, when they say a complex root, they probably mean an imaginary root. So in other words, not the solution 1. It's one of the other 4. But we don't know which one, and it doesn't matter which one. It doesn't matter which one we pick. It turns out that the w squared, cubed, power of 4 and power of 5 will turn out to be the other ones. So how do we show that? Well, z to the power of 5 is equal to 1. We know that. That's the equation we were solving. And we're saying w, or omega, is a solution. So therefore, if I sub it in, it's got to be correct. So I now know omega to the power of 5 is equal to 1. If I raise omega to the power of 5 to the power of 5, I would get 1 to the power of 5. And that's 1. So therefore, omega to the power of 5 is a solution. So, okay, that proves omega to the power of 5 is a solution. I could do the same with squareds. If I raise omega squared to the power of 5, that would be the same as getting omega to the power of 5 and squaring it. But we know omega to the power of 5 is 1, and 1 squared is 1, so therefore omega squared solves the problem. So omega squared is a solution. Omega cubed to the power of 5 I could rewrite as omega to the power of 5 cubed. And omega to the power of 5 we know is 1. And 1 cubed is 1. So yes, omega cubed is a solution. Omega to the power of 4 to the power of 5 is the same as omega to the power of 5 to the power of 4. And we know omega to the power of 5 is 1, and 1 to the power of 4 is 1. So omega to the power of 4 is also a solution. So what we're showing there is it doesn't matter which one we pick, we just call it omega, and we say this is a solution. We can manipulate using the index laws and show all the other ones will be solutions. It doesn't matter what omega is. The other ones will also be solutions. So therefore, if omega is a root, so will omega squared, cubed, power of 4, and power of 5. They'll all be solutions to this equation. This is a fun little question. It's a common question. Prove that 1 plus omega squared plus omega cubed plus omega to the power of 4 is equal to 0. And there's actually a few ways we could do this. First thing I could do is I could say, well, hang on, they're the roots. We just showed they were the 5 roots of this equation. So the sum of the roots would be minus b on a. But our equation, if I rearrange it so it equals 0, is z to the power of 5 minus 1 is equal to 0. So b is 0. There is no coefficient of z to the power of 4. So they equals 0. And the only other thing I did there was so I could solve the question is I said, oh, and I know omega to the power of 5 is equal to 1. And there's my solution. So that's a very quick way of doing it. There's another way of doing it. There's the equation. We know omega is a solution, so I can sub it in. So it's true to say omega to the power of 5 minus 1 is equal to 0. I'm going to factorise that. Remember when we said a to the power of n minus b to the power of n. We start off with a minus b, in this case omega minus 1. Then we go, the powers of omega will go down by 1. The powers of 1 will go up by 1, although I've written it backwards there. So the rest of it would be 1 plus omega squared plus omega cubed plus omega to the power of 4. Right? So it comes from that idea. Right? A to the power of n minus b to the power of n. B in this case is 1. Well, therefore, 1 plus omega squared plus omega cubed plus omega 4 must equal 0. Because omega can't equal 1. Remember? We said it was a complex solution. So we know it's not equal 1. Omega minus 1 can't equal 0. Therefore, the other bit must equal 0. There's another way. Here is the expression 1 plus omega squared plus omega cubed plus omega to the power of 4. That's a geometric series. So its first term is 1. Its ratio is omega. Number of terms is 5. So subbing into a r to the power of n minus 1, I get omega to the power of 5 minus 1 over omega minus 1. But hang on, omega to the power of 5 is 1. So therefore that's 0. So 3 different ways we could solve that particular problem. Now this is the sort of thing, in some of the roots question, if they don't specifically ask me this, then I can quote it. When we're solving roots of unity questions, basically there's 2 facts that we use when we're playing with the algebra. One is that omega to the power of whatever is equal to 1, or minus 1 as the case may be. And the other thing we use is 1 plus omega squared plus da 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 up to the last one is equal to 0. Using those 2 facts, we can manipulate and solve all these different types of questions. So something like this. Find the quadratic equation whose roots are omega plus omega to the power of 4 and omega squared plus omega cubed. Now they've picked those pairs very purposely. Because if you notice the pairs, the powers add up to be 5. They would turn out to be conjugates. Yeah, they turn out to be conjugates. But anyway, so let's have a look. I'm going to create a quadratic, so I need to know its sum of the roots. Sum of the roots would be omega plus omega 4 plus omega squared plus omega cubed. But we just proved that 1 plus omega squared plus omega, etc. is equal to 0. So therefore, this expression must equal minus 1. We're just moving the 1 to the other side of what we just proved. So that's the sum of the roots. Product of the roots. If I expand that all out, but hang on. Omega to the power of 6 is the same as omega. Because remember, omega to the power of 5 is equal to 1. And omega to the power of 7 is the same as omega squared. Because omega to the power of 5 is equal to 1. So therefore, we have the same expression again. That is equal to negative 1. I now know the sum of the roots. I know the product of the roots. So my quadratic must be x squared plus x minus 1. Minus the sum of the roots x plus the product of the roots. So there's our equation that we're looking for. All right, we're told this time it's a cube root of unity. They've in fact given us the nice little equation. We don't have to prove it. They told us we can use it. So we know 2 things. We know 1 plus omega squared is equal to 0. The other thing we know for this one, because it's a complex cube root of unity, omega cubed is equal to 1. They're the 2 facts that we know. Evaluate 1 plus omega squared all cubed. Now, the temptation is to expand the whole thing out. Not going to do that. Because 1 plus omega squared is the same as minus omega. Because remember, 1 plus omega squared is equal to 0. Minus omega cubed is a lot easier to cube than 1 plus omega squared. That's minus omega cubed, but I know omega cubed is equal to 1, so that's minus 1. If you had expanded the whole thing out, and then you would have played with some different terms, you might have had to turn an omega 5 into an omega squared and things like that, but it will drop out. But the idea here is, if I've got 2 terms cubed, it's always easier to cube 1 term than it is 2 terms. So I manipulate that expression over there, 1 plus omega squared equals 0, to turn 2 terms into 1 term. This algebraic fraction, temptation is to get a common denominator and then play with the fraction. Not going to do that. Again, the denominator has 2 terms. A lot easier to deal with fractions when the denominator has 1 term. Well, 1 plus omega is the same as minus omega squared. And 1 plus omega squared is the same as minus omega. So now my question is minus 1 on omega squared, minus 1 on omega. That's a lot easier to add. So that becomes minus 1 minus omega on omega squared. But hang on, minus 1 minus omega, I can manipulate our expression. That's omega squared. And omega squared on omega squared is 1. Now, it's at this point you're thinking, this is easy. All I've got to do is write down 1 or minus 1, and I've got a 50-50 chance of getting the answer. I don't think you're going to get the marks for that. They're looking for the manipulation to see whether you know what's going on here. We're now going to create a cubic equation whose roots are 1, 1 plus omega, and 1 plus omega squared. Well, I could do it this way. I know that 1 is a root, so therefore z minus 1 is a factor. That's one factor worked out already of this little cubic equation. The question now is, what is the quadratic? Well, we've got a quadratic whose roots are 1 plus omega and 1 plus omega squared, which I can do. Minus the sum of the roots becomes 2 plus omega squared. Hang on, I know 1 plus omega squared is equal to 0. Therefore, that's 1. And when I expand out the 1 plus omega squared, I get 1 plus omega squared plus omega cubed. Hang on. 1 plus omega squared, I know what that is. That's 0. Omega cubed, I know what that is. That's 1. So therefore, I've got z squared minus z plus 1 equals 0. I said I could do it that way. There's a quicker way. Because if this root is 1 plus omega, which is 2 terms, I could have said that root was minus omega squared, 1 term. And 1 plus omega squared, I could have said that root was minus omega, 1 term. And then it's a bit easier to work out what's the sum of the roots, what's the product of the roots. Okay, I've expanded it out to see what this equation actually is. So that's where it is, factorise, expand it out, group terms together, and that's what we end up with, z cubed minus 2z squared plus 2z. Oh, what nice symmetry we have there. We're going to solve this equation. Z to the power of 5 plus z to the power of 4 plus z cubed plus z squared plus z plus 1 equals 0. That looks pretty hard, so I'm not going to do it. I'm going to solve a different equation, which is a lot easier. I know z to the power of 6 minus 1 would be z minus 1 times z to the power of 5 plus z to the power of 4 plus z cubed plus z squared plus z plus 1. And z to the power of 6 minus 1 equals 0 is a lot easier to solve because that's a roots of unity question. So I know z to the power of 6 minus 1 has these solutions. Cis 2 pi k, where k equals, first solution would be 0, which is of course 1. And then I have conjugate pairs, plus or minus 1, plus or minus 2. I need one more, so I'll use 3. So therefore, this particular equation must have the same solutions, except one of them. Which one? Right. Because that's the one I introduced. Z minus 1 equals 0. So I know the 6 solutions of all this. Well, 1 is the solution to z minus 1 equals 0. Therefore, the other 5 must be the solutions to z to the power of 5 plus z to the power of 4 plus and so on and so on. So to make it a little bit clearer, I could multiply top and bottom by z minus 1. We know the solutions to the top, however, bottom of the fraction can't equal 0, so z can't equal 1. So that's another way of thinking about it. So I can say, all right, it's the solutions of z to the power of 6 minus 1 equals 0, but not including z equals 1. That one is not a solution. So I have cis pi on 3, its conjugate, cis 2 pi on 3, its conjugate, and cis pi. And if I was to convert all those, because they are exact values, so we could work those out quite easily. Half plus root 3 on 2i, and minus root 3 on 2i, minus half plus root 3i, and so on. Mind you, actually, before I go on to the next one, I could have also drawn a picture to find those solutions. 6 solutions. I know a solution is 1. I'm going around. What shape am I going to draw? Well, yeah, I'm going around the circle, but the actual shape on the circle when I join the solutions up, going to be a hexagon. So it's going to look, they're going to be the conjugates, they're going to be the conjugates. That obviously is minus 1. What's the size of the angle that I'm going around? Yeah. So that angle is 60 degrees or pi on 3. So therefore, that is cis pi on 3. That is cis minus pi on 3. That is cis 2 pi on 3. That is cis minus 2 pi on 3. And there's our solutions. Okay? So that's another way of finding them, is using the symmetry of our shape. Okay, let's have a look at this one. Ooh, old question. They have told us omega is cos 2 pi on 9 plus I sine 2 pi on 9. They want us to show that omega to the power of k. This is essentially the same question, because what they're really saying is, well, if omega is a solution, then omega to any power is also a solution. And that's what they're saying, where k is some integer. So I'll do it the same way I did before, but I can do it actually a lot nicer than the way I did before. I don't have to go and show how I manipulated the indices. I don't have to do it for 1, 2, 3, 4, 5, 6, 7, 8. I'll do it this way instead. Z to the power of 9 is equal to 1. Because they've told me the specific solution of omega, I can do it a lot quicker. So therefore, Z is equal to cis 2 pi k to the power of 9, where k equals 0, 1, 2, 3, 4, 5, 6, 7, 8. Well, by de Moivre's theorem in reverse, I could say cis 2 pi k on 9 is the same as cis 2 pi on 9 to the power of k. Oh, cis 2 pi on 9, that's what they said omega was. So there you go. Omega to the power of k is a solution when k equals 0, 1, 2, 3, 4, 5. In fact, any integer you like. Remember I said I could pick any integer as long as we picked consecutive ones. So any integer will solve that problem. There's the standard one. Looks a little bit different because they haven't said equals 0. Ooh, those tricky people. They moved the 1 to the other side. So we got to prove omega plus omega squared plus... righto. Which way did I choose out of all the ways I went? There's our equation. Therefore, because sum of the roots. Sum of the roots will equal 0 in this one. Okay. Oh, but of course, that doesn't answer their question. Now I've got to be tricky and move the 1 to the other side. Hence show. 3 things multiplied together equals minus, positive an eighth. Similar to the one yesterday, isn't it? Similar. Okay. This is how I'm going to do this one. Z to the power of 9 minus 1. I now know factorizes to be z minus 1, z minus omega to the 8, etc., etc., etc. And you might think, that's a rather odd way to write it. Wouldn't you go omega, omega squared, cubed, and so on? But I've grouped what I know to be conjugates together. The conjugates are where the powers add up to be, in this case, 9. So I've got z minus omega. I've grouped it with omega 8. So I'll put those two together. they will create a nice quadratic. Squared and 7 will create a nice quadratic. Cubed and 6 and so on. So what I do know is that those quadratics will be minus the sum of the roots plus the product of the roots. Now, we're talking about roots of unity. Product of the roots are always going to be 1. So I know in each of those parentheses I'm going to end up with plus 1, because I have to multiply the whole thing out, if you like, and get minus 1. Now, how did I get these middle terms? Remember, we know the solutions. We said if omega was a solution, so is omega squared, cubed, and so on. But omega was cis pi on 9. So this one here is cis pi on 9. Its conjugate, therefore, is cis minus pi on 9. If I add the two roots together and their conjugates, I get twice the real part. The real part in both of them is cos 2 pi on 9. Then the next one, 4 pi on 9. The next one, 6 pi on 9. And the next one, 8 pi on 9. So I've got cis 2 pi on 9 times cis the conjugate. If I get them together, I'm going to get z minus twice the real part of cis 2 pi on 9 plus 1. Okay. What is the real part of cis 2 pi on 9? So I get, we are trying to get cos pi on 9 times cos 2 pi on 9, cos 4 pi on 9 out of that expression there. I know this to be true, that z to the power of 9 minus 1 is equal to this. 6 pi on 9 is 3 pi on 2. What's the cos of 3 pi on 2? 2. 6, we'll try that again. 6 pi on 9 is 2 pi on 3. What's the cos of 2 pi on 3? So I've got minus 2 times minus half is plus 1. So I've done that one. Okay. So because I had an exact value in there, I've substituted in for the exact value. I'm going to let z equal I. Watch the magic happen. So, left-hand side becomes I to the power of 9 minus 1. Right-hand side becomes I minus 1. But have a look what happens in each of the parentheses. In each of the parentheses I have z squared plus 1. Z squared now becomes I squared. And I squared plus 1 is 0. And I now have ended up with a product of these causes. Boom. This is a bit awkward, the I minus 1. But hang on, I to the power of 9 is I. So, they will cancel. I've also taken the I to the power of 4 out as a factor, because have a look. Each of these have I as a factor. So I've taken that out. But I to the power of 4 is equal to 1. So I can now say negative 1 is equal to 8. 2 times 2 times 2. 8 times the cos of 2 pi on 9, cos of 4 pi on 9, cos of 8 pi on 9. We're almost there. What they asked didn't have a cos 8 pi on 9. 8 pi on 9 is in the second quadrant. So it's the same as the negative, the cosine of the acute angle, pi on 9. So negatives now will cancel. We have our solution. Is that fun or what? Why did I do that? Is the question that's being asked. Okay, I want to end up with a product of cos, cos, cos. I've got products there, but there's other things that are in the way. But those other things are z squared plus 1. I can make z squared plus 1 go away if z is I.